today we can discuss about that gas chromatography. Different. This is called the different types of classification of the chromatography. What is the versatile technique? This is the most useful for the chromatography technique for the in the gas chromatography. What is the most gas chromatography is undoubtedly the most important and extensive applied technique because the analytical and as well as the industrial purposes. This is the most important for the industrial purposes. The most that's why this most wide applications in analytical technique in gas chromatography. Gas chromatography is always chromatography developed by 1941 by A.Z.P. Martin, R.L.M. Singe, that is called a Singe scientist got the Nobel Prize in 1952 from the discovery of gas chromatography. How to get the Nobel Prize? Discovery of chromatography means that is the most that is the source of invention of that technique. That's why here to Singe got the Nobel Prize. That's why there is the most important analytical method. A.P. James Martin 1952. First, they are separating the fatty acids by this technique. This is first separated fat. This most successful story in the gas chromatography by using the fatty acid separation. Almost all fatty acids are separated by using the gas chromatography. It is rapidly becoming an important process for the controlling the plants. Control method in the chemical plants and refineries. Important process in the control method. Chemical plants, how to control in the chemicals, where which concentration you have to supplying of the first step to the another step to the another step. With the controlling of the all the parameters and the refineries, oil refineries, we have to use the gas chromatography. What is the basic principle involved in the gas chromatography? In the gas chromatography is used in the stationary phase, either the solid or liquid, and a mobile phase is gas. Gas chromatography is the mobile phase is the gas. That's why here that is called as the gas chromatography. Stationary phase, either the solid or liquid. Solid or liquid. That is the gas chromatography. These are the two phases. In every chromatography have the two phases. One is the stationary phase, mobile phase. In the gas chromatography, mobile phase is the gas. Stationary phase is the either solid or liquid. When the gas is the vapor comes to the contact with the adsorbent, certain amount of it gets adsorbed in the solid surface. The phenomenon occurs in the according to the Freundlich adsorption law or Langmuir adsorption law. We know about the Freundlich adsorption law. X by m is equal to Kc to the power of 1 by n, or Langmuir law, x by m is equal to K1c plus K2c, where x is the mass of the gas or vapor absorbed mass m of the absorbent, c is the vapor concentration of the gas phase, K1, K2 are the constants. If the gas vapor comes to the contact with the liquid, a definite amount of gets dissolved in the liquid according to the Henry's law, partition x by m, that is equal to Kc. The different sorbents are there. In gas chromatography, vapor is contact. What is the basic principle? Whenever the vapor is contact with the adsorbent, it contains certain amount of gas adsorbed on the solid surface. That is a phenomenon occur. How much gas is adsorbed in the solute? That is according to Freundlich and Langmuir adsorption term. In gas chromatography refers to the physical process by which the mixer is separated. Mixer is separated into its constituents by moving gas phase passing over a stationary sorbent. The mixer is separated into constituents by moving gas phase passing over a stationary sorbent. Based on that nature of the stationary phase, the gas chromatography can be subdivided into the gas solid chromatography. These are the two different gas chromatographies are there: gas solid chromatography and gas liquid chromatography. Gas is the most common, G, first letter G, that is called the mobile phase is gas. Stationary phase is the solid, that is called the gas solid chromatography. Stationary phase is the liquid, then it is called as the gas liquid chromatography. In GSC, gas solid chromatography, stationary phase, in the stationary phase, solid, active solid adsorbent such as the granular silica, alumina or carbon. In GLC separation occurs that partition sample. A sample between the mobile phase and a thin layer of the non-volatile liquid wall of the capillary tube. Typically, the stationary phase is sufficient. Always stationary phase is a low vapor pressure at the column temperature, so that it considered as the non-volatile. How it is considered as the non-volatile? That is the sufficiently low vapor pressure at the column temperature, so that it can be considered as the non-volatile. Sample mixer gases, generally in gas chromatography, in sample mixers of they run through the column with carrier gas, that is called the carry means one from to the another. We have to call it as the carrier from hydrogen, helium, and nitrogen. The sample mixer from the run through the column, we have to call the column. Separation can be achieved by the differences in the distribution ratios of the components of the mixer and sample between the mobile phase and the stationary and the liquid phases to move through the column at different rates of that one. We have to causing the move through the column at different rates. That is called the different retention time. Maybe whenever the using of that mobile phase, always the retention time. After elution of that sample, the can be detected, can be exit between the mobile phase and stationary phases. Separation, always differences in the separation ratios of the components in that sample. What is the theory of gas chromatography? Is there any gas chromatography theoretical process there? Yes, there is the theoretical process is there. The controlling of the three physical transport phenomena, that is called the biflow, by for three physical transport phenomena, that is by flow, by diffusion, and by interchange of the material between the mobile and the stationary phase. We have to take the by flow. Flow is the most important for the gas, and diffusion is also most important, that is called the separation. The interchange of the material, we have to take that material between mobile phase, interchange of material between the mobile phase and stationary phase. We have to take that one. The most important between the distribution between the solute between the two phases, as the solute introduced into the column. The most important phenomenon, the distribution of the solute between the two phases. The solute is introduced into the column. The molecules are distributed between the mobile phase, that is called the carrier gas, and the stationary phase molecule. A dynamic equilibrium is thus established. The molecules pass between the liquid and the gas. This is the most important in the gas chromatography, that is the equilibrium is thus established. The molecules pass between the liquid and the gas, because the gas is the mobile phase, liquid is the stationary phase. The equilibrium is established, the molecules between the liquid and the gas. Whenever the equilibrium is obtained, the concentration of the molecules each type is a constant ratio of the two phases. Whenever the K is equal to concentration of the molecules in the liquid phase by concentration of the mobile in the mobile phase. This is the K. K is the concentration. Suppose you have to take the greater value of the K, concentration of the liquid phase, the more solute will be dissolved, greater will be the value of the K, greater concentration. Alternative, you have to increase the concentration of the liquid phase, then automatically the result of the increase the residence, that is called time partition ratio of the increasing. How is there any gas chromatography depends upon the column. Column is the most important. Column is the heart of that gas chromatography. That is called the efficiency of the column. Efficiency of the column is most important for the gas chromatography. Suppose the efficiency is not so good in the your gas chromatography is not perform is not very good. That's why we have to always the column efficiency is very good. Yeah, how to know the efficiency of the column? That's why you have to expressing that column efficiency by using the number of theoretical plates, that is called capital N by the height of the equivalent of theoretical plate HETP. The larger number of theoretical plates, the smaller HETP. The more efficient the column is for the separations. That's why you have to the more efficient of the column separations by using the larger number of theoretical plates, smaller the HTP. That's why from the elution curve, the number of theoretical plates in any column will be calculated. This is called the height, 0 to 10 height, volume, value to time short distance. We have to calculate the HTTP. These are the distance D. This is a D from the point of injection to peak that maximum can be measured units of length, time and volume. It is generally called retention volume, VR, retention volume. H is called height of the peak of the, this is called H, called the height, this is called the H, this is called the height of the peak of the maximum. W is called the width of the peak measured as the distance between the intersection. That is called the intersection of the tangents. Tangents means this one. Tangents or the inflections of the point baseline. B is the width. B is the width of the peak of the height h by e. T is the time of the lapse. T is equal to time, small time. T is equal to time. T is the time lapse between the injection and the initial rise of the peak, return of the peak, baseline respectively. Height multiplied the width of the peak, one of the height. This is called calculation. That is called the Van der Meer derived an equation that is called capital H is equal to 2 lambda dp plus 2 lambda dc by mu plus 8 by n square k by 1 plus k whole square d square of a dl mu. That is equal to, in all these parameters you can call it as A. This is called the B by U plus this is called C, where U is the gas viscosity, that is called the flow rate of the gas. A is a constant and involves the packing of efficient column and the practice diameter and is called the eddy diffusion of the HETP. What is the instrumentation of the gas chromatography? This is a good instrumentation for the calculation of the parameters in the all the components present in that particular sample, where GLC and GSC consist of 6 basic components. This is called carrier gas, most important. We maintain the always high pressure and derive the instrument rapid and reproducible rate. In the sample injection, the separation column, one or more detectors, and another one is the thermostated chambers. Thermostated chambers are the most important. We have to use the temperature regulation of the column detectors, and amplification of the recorder system, an amplification and recorder system. This is the flow diagram for the schematic diagram for the gas chromatography. We have to take that this is the gas regulators are the gas regulator. High pressure will be applied, the reference flow meter, and then a simple flow meter. This is called the column. This is the most important for that your gas chromatography. The number of theoretical plates also. This is the gas. We have to apply this gas. We have to give in the gas flow from one place, this place to this one. You have to inject the sample, and then the sample carry that gas. The diffusion will occur in that particular column. In that particular whenever the sample is diffusion, slow particles one by one, that is solid particles will be slowly moved from this direction, and then easily sample will be detector. That is by using the detector bridge. We have to use that bridge to amplify, and then we have to recorder by using this software technique. By using this we have to calculate the how much quantity present in your sample by using this one. This is a reference flow meter. This is called, these dotted lines is called as the thermostat. You always the why you are using this thermostat in the column, because thermostat present in that particular column is always maintain the temperature should be constant. Temperature should be constant. So that's why you have to using that particular thermostat for particular column. Column is a W shape or U shaped maybe. Yes, this is the schematic diagram for the gas chromatography technique. The column, already we have to take the column. Most columns are 120 centimeters to 5 meter length, 2 to 10 diameter. So diameter will be 2 to 10 millimeters, and the length will be 120 centimeters, 5 meters. Column effects. Columns are made with the stainless steel. It is made up of the stainless steel and copper or cupronickel, glass or plastic, and maybe coiled or U or W shape. Whenever the glass or plastic or maybe coiled or in U shape or W shape, the columns. Metal columns are expensive, are very big because they are stout and inert, possess the good thermal properties. These are the column present. Types of the columns is present. Adsorption columns are present at room temperature. That is called more work efficiently. Adsorbent silica gel. Adsorbent metals used for separating gases. Silica gel gases are carbon dioxide, methane, ethane. Just like that, activated carbon adsorbent. We have to gases is the hydrogen, oxygen, nitrogen, carbon monoxide, and O1 methane gases. Adsorbent is alumina. We have to gases the methane, ethane. That is called C2H6. Lintel sieve 5 amperes. That is called H2 hydrogen, oxygen, nitrogen, carbon monoxide, methane. Just like that, we have to use the adsorbent or the different gases are used. That is adsorption column. And then the another one is column length 100 grams. Sieve size is 120 to 140, and 200 centimeters, 100 centimeters 120 to 240, 200 centimeters to 80 to 100 sieve size. Column length 5 meters to 50 to 60, 10 meters to 35 to 45. And the partition columns. Partition columns is the GLC, gas liquid chromatography. Partition columns are the packed with the inert support carrying the non-volatile liquids, non-volatile liquid phases. For separating these are used for the separating the hydrocarbons and ethers, ketones, halides, and olefins. Capillary columns also present. Is there any detectors? How to in your schematic diagrams in the sample contains is no more solutes. How to detect? These are the more detectors are present, and the detectors are measure the small amount of the separated components present in carrier gas stream leaving the column. Whenever the accuracy of any gas chromatographic analysis depends upon the property, that is called sensitivity. Q mini is equal to Rn by S, where Rn is the noise level. With the noise level we can detect linearity, stability, and we have to use the universal select detectors. Types of detectors are there. There can be two types. Detectors responding from the solute 1 mole fraction of the carrier gas. Detectors can be respond flow rate of the solute. Mainly three types of detectors: thermal conductivity detector, gas density detector. Another one is the ionization detector. In ionization detectors are the so many detectors are there: flame ionization detector, rare gas detectors, organic ionization detectors, element select detectors, flame photometric detectors, flame thermocouple detectors. These are the all the different types of detectors will be. By using the what is the use of that gas chromatography? These are the lot of uses for this gas chromatography uses. There is a separating of the organic acids by using the chromatography. Neither chromatography is standard method for the amino acid analysis. Most of the 12 amino acids are easily separated by using this technique by gas chromatography. Is this technique for gas chromatographic separation by mixture of the trifluoroacetylated amino acid methyl ester? We have to take that one. Uh, cysteine, cysteine, arginine, tyrosine, cysteine, arginine, tyrosine. We have to just like that. We have to all the amino acids are separated by using this gas chromatography. Thermal conductivity detector. These are the different types of detectors in our scenario in the graduation level. TCD, that is called the non-destructive concentration sensitive detector that responds to the difference. We have to concentration is more, automatically sensitive detector will be more. So suppose concentration is very less, that is the detector will be slowly detect thermal carrier gas and the carrier gas containing the sample. In generally used detector permanent gases, light hydrocarbons and compounds can be poorly to the FID, flame ionization detector. This is called the switching slow off. This is called filament ecant. This is called flow in this direction only. Switching flow ion column flow to the make up that one. This is called the ionization detector. TCD thermal conductivity, is there any heat is more, and then automatically that will be sensed, or light hydrocarbons will be detected by using the thermal conductivity. By using this technique in the gas chromatography, separation of the chlorinated hydrocarbons. Chlorinated hydrocarbon, let us consider we have to take the this is called the retention time, x-axis. In the y-axis we have to detect a response is there in gas chromatography. You have to take the 0 hexane, one is the 0 that is called hexane, and one is the lenadine, second one is the heptachlor, third one is the telodrine, fourth one is the r-chloridine, that is called the endosulfone, and sixth one is the P dash in the DTD. This is the separation of the chlorinated pesticides dissolved in hexane. These are the solvent is used for the hexane. In the chlorinated pesticide is separated by using that gas chromatographic technique. By using application the qualitative analysis and as well as the quantitative analysis. In qualitative analysis, we have to use it there. In industries, ultra sensitive detectors, GC for the useful field of detectors, and quantitative detectors also salute the recording chromatographic techniques. We have to use the sharp narrow peaks. We have to calculate the peak areas and then calculated the analysis. In the elemental analysis, we have to GC in the determination of elemental analysis carbon, hydrogen, nitrogen, oxygen, and sulfur. Organic and non-organic metallic samples, we have to use that already detectors by using the different types of detectors. And the determination of the sulfur, we have to detect the sulfur is present in that particular sample by using the gas chromatography. And also most important for the determination of total organic carbon. Total organic carbon TOC is important in water analysis. How in water analysis monitoring of the indication of the organic pollutants, water is acidified with purchase to remove the carbon dioxide from a carbonated bicarbonate present in most of the industrial wastewater and industrial water. We have to use the gas chromatography technique and monitoring of the all these parameters. We have to converted juicy flame ionization detector, very useful in the gas chromatographic technique. By using the gas chromatography technique, lot of helpful for the global need for the versatile technique for the lot of pollutants and lot of analysis for you have to use that one. This is the gas chromatographic technique.